Voilà. Theo is here.
It's good. Okay, so good morning, everyone, and good morning, Theo. It's a great pleasure to be here and to lead the jury committee. And you are going here to defend your PhD entitled Studies on Inorganic Solid Electrolyte for Batteries, focus on sodium 3PS4. But prior to give you the floor, let me present the jury. We have first Mark Wajmaker, who is professor at the University of Delft, and he has been really looking at your PhD and reporting on your PhD. Gwenal Roos, which is a Met conference at the Collège de France, was also looking at your PhD and report on it. Then we have Laurence Krokonek, that is a research director at the CNRS in Bordeaux. You have a professor, Wolfgang Zeyer, at the University of Münster. You have Jean-Noël Chotard, that you know very well, of course, at this Metro conference that has been working with you. And Christian Masquelier, which has been your director of the thesis, and Saiful Islam from University of Bath, and which we have been very collaborating in this co-share PhD in the case of Alisto. So, and myself, which I am professor at the Collège de France. So I think, Theo, you have about 45 minutes to tell us what you have been doing, and then we'll go to questions. Thank you.
Thank you. I hope everyone can see and hear me correctly. If not, I guess shout or something. Yeah, from wherever you're watching, I hope you're comfortable. In fact, I hope you're as comfortable as I am uncomfortable presenting in an empty room. I guess we'll call that it's not empty. The principle of conservation of comfort, last minute addition to my PhD. Well, but okay, we're not here for jokes. We're here for solid electrolytes and for any 3PS4. So before I jump into that, just quickly give you a geographical description of my PhD. I've been funded for 3 years from Alistair to do a PhD between the LSS in the north of France and Amiens.
Could you speak louder?
I can bring the microphone closer.
Yeah, sorry, please, it will be nice because.
Is it better?
Great, you can. Thank you.
Is it better now then?
Oh, yes.
Okay.
Yeah, much better.
Yeah, much better. Yeah.
So I was saying that the first 3 years were funded by Alistair between the University of Picardie in North France in Amiens in LSS, and then with frequent visits for collaboration on computational chemistry with the University of Bath. And then I did a 4th year, which was funded by a scholarship of the German Academic Exchange Service in the University of Gießen and the working group of Professor Zeyer. And within those 4 years, a lot of visits for beam time at large-scale facilities for neutron and synchrotron X-ray experiments. Right, so this work has been done in the framework of battery research. So I will quickly explain the context there. So starting from the current state-of-the-art, commercially and technically, lithium-ion, which is composed by 2 materials, anode and cathode, and a liquid electrolyte whose job is to shuttle the ions back and forth and produce current. So when we're talking about a solid-state battery, simply what we're talking about is replacing the liquid electrolyte with a solid one, shown here by the yellow bubbles, which then renders the battery all solid. It's important to note at this point that this concept, in contrast to other post-lithium-ion concepts, does not directly increase the energy density of a battery, which is somehow the de facto criterion for competitiveness. But we use this as a sort of way to enable high-performance electrodes that is shown here for lithium metal, which could, in theory, increase the performance of the battery through its higher energy density. So if we look at this cartoon here in the middle, you can already see some of the problematics that come when you make the battery all solid, when it's essentially a composite of a lot of different solid materials. Basically, what we're going to have to look at is the ion transport now as a multi-scale process. So if we look at the left end of the scale, the small end of the scale, there have been many advances in the last few years from computational techniques where we look at the atomic structure of material and describe the energetics and the dynamics of hopping ions. On the other hand, most experimentalists more work on the totally other end of the spectrum, on the right here, characterizing what I would call here the macroscopic conductivity of electrolytes. But if your electrolyte is a solid, you introduce a lot of effects on the mesoscale between those two extreme scales. So you will have crystallites with preferential orientations, you will have grain boundaries that can have their own resistances, you might have amorphous phases, impurities, and the distribution of all of these in space will give rise to this mesoscale conductivity. As an addition, when you're trying to contact your electrolyte with electrode materials, you're going to have to an issue that does not exist in lithium ion, where the liquid electrolyte can simply wet all the solid parts. So you're going to have problems of contact area. So basically, all these mesoscale aspects in between are somehow the elephant in the room, in the sense that everybody understands that they're important, and in that sense they're blocking further advancement, but they're hard to accurately look at either by computation or experiment. Nevertheless, the last 10-15 years of research have allowed us to discover and study in detail a lot of solid electrolyte families with respect to their high ionic conductivity, which is what I'm plotting here from the recent review. Typically, we talk about families as a function of their composition, their chemistry, and their crystal structure. So you see different families shown here, and what is important to highlight is that we're now at a point where we know of a few different, actually, families of materials that can reach the ionic conductivity of liquid electrolytes and can, as such, be envisioned as battery electrolytes. So during my thesis, we investigated a number of different electrolytes. I'm showing here some examples. For example, the Theodosios family and its archetype Li3PS4, LPS glass ceramics in collaboration with a recently defended PhD. The oxy-sulfide orthophosphates, which was the original goal of my thesis. Antiperovskite, which is a very, let's say, novel family of materials that I had the pleasure of investigating through my supervision of two master's students here in LSS. And finally, finally, what I will call here the Na3PS4 family of materials, which can, in essence, the phosphorus can be any pnictide, antimony, arsenic, and so on. The sulfur can be substituted by selenium, but they're all isostructural in the Na3PS4 archetype. And this is basically the focus of my talk here today. So why do we care about this Na3PS4 family of materials? I will highlight here what I think is the two key advantages. One is a distinct moisture tolerance of these materials, which is not a given if you compare it to other solid electrolytes which decompose in contact with air or water. And this is also, I think, very interesting on an upscaling point of view, because we can then envision an aqueous synthesis that would be readily scalable and cheap. I show here, for example, Na3SbS4, which simply forms a hydrate when exposed to air and can simply be dehydrated by heating it up. So it does not decompose in contact with moisture. And finally, the Na3PS4 also contains the materials that are, let's say, the record holders for ionic conductivity in a polycrystalline form. And this was shown very recently through tungsten doping of the antimonate, which presumably introduces vacancies into the structure, increasing the conductivity to the levels of 40 millisiemens per centimeter. So with that, I would like to very quickly describe the state of the art on Na3PS4 right before my thesis, 4 years ago. The first work considering Na3PS4 as a solid electrolyte was performed by Martin Janssen in 1992, who solved the room temperature stable ground state alpha in the tetragonal space group. He also showed that there's a cubic polymorph appearing upon heating above 250 C. And using these thermograms shown here, they observed this bizarre doublet peak, which they assigned to melting. And they hypothesized also that there might be a second polymorph appearing right before melting. Very interestingly, however, they mentioned in this paper, and I'm quoting directly, it should be mentioned that the mechanical stability was good up to the melting point and still satisfactory above 570 C. So this raises some questions as, is the melting actually at 500, which I'll come back to. So we have 2 + 1 polymorphs, and they measured a conductivity of the order of 10 to the -6 Siemens per centimeter, which is somewhat low in view of practical applications. The material was somehow stayed in the dark for a little bit. Just to drive the structure home, I'm showing here a series of diffractograms that were taking temperature on the y-axis. So basically each line here represents a diffractogram. The yellow highlights the Bragg peaks. You can see very well that we have a single phase up to about 250 C, and then some characteristic peak merging and peak extinctions that are characteristic of a second order transition from the alpha to the beta phase. The structures look like this. Basically, they're very related, as you can see. We can be described as a body-centered cubic arrangement of the PS4 tetrahedra, shown here in purple. The difference between the two essentially is in the tetragonal model, the sodium positions need to be described by 2 crystallographic sites, distinct ones. And then in order for the transition to happen, this second sodium site just needs to shift along the C-axis. And simultaneously, a small rotation of the PS4 anion needs to happen also about the C-axis to get the perfect cubic symmetry. Before I move on, you can see, if you look back at the diffractograms above 500, something interesting is happening. That is not exactly what you would expect from a melt, but I'll come back to that later. So the reinvigoration of the interest in Na3PS4 came 20 years after the first study by Janssen, from the work of Akitoshi Hayashi, who showed that if you produce the same material, Na3PS4, by ball milling, you can significantly reduce the resistance, as shown in the impedance spectra here. So increase its ionic conductivity. They showed that the ball mill material actually exhibits the beta phase, so the high temperature phase, stabilized at room temperature, in contrast to the alpha phase, the tetragonal phase that you get from a typical solid state synthesis. And they hypothesized that this is the reason why we see such a high conductivity. They use this material that now has a usable conductivity to demonstrate the first working sodium batteries based on Na3PS4, shown on the cycling here. And this whole effect of the ionic conductivity enhancement has been reproduced multiple times in the literature, at least 10, 15 papers. I'm just showing here an example from the group of Thyssen, where you can again observe the 1 order of magnitude increase upon ball milling the material. So from this quick state of the art, I generated a couple of questions, and we can look at it both from a practical point of view and a fundamental point of view. So on the practical side, it's very interesting to understand what leads to the conductivity increase when you ball mill a material like Na3PS4. So what is really the magic of ball milling? Could we ever reach the same high conductivity without mechanochemistry? From the fundamental side, do we really have a complete understanding of the structure of Na3PS4? Are all the phases completely characterized? And do the dynamics of the thiophosphate anion contribute somehow to the conductivity of sodium? So we answered these questions in this thesis by variable temperature and pressure, experiments and simulations. And I will start here first from what I call here the practical view, looking at the ball milling effects. So I will do this by comparing three samples. The first one is a solid state synthesized sample, which will be denoted in red, high temperature tetragonal. And the second one is a mechaноchemically synthesized sample, which I denote here PM cubed in blue. We also synthesized an intermediate sample inspired by previous studies, which is basically the ball mill sample subjected to a very short annealing at high temperature. So let's first have a look at the diffractograms. You will recognize the tetragonal phase through these distinct peaks and doublets. So we get the right material from solid state synthesis on the top. From ball milling, we actually get the cubic polymorph. Again, you see that the peaks denoting the tetragonal phase are not there, and the doublets have now merged. And the intermediate synthesis also stabilizes the tetragonal phase. You can see directly from the positions of the Bragg peaks, if we do a quick fit, that there is quite a bit of a difference in volume from the cubic sample. So the two tetragonal samples are more or less the same, but the mechanochemically synthesized samples shows a lower volume. We went on then to analyze the shape of the Bragg peaks to get microstructural parameters for our powders. And this is better shown in what is called the Williamson-Hall plot. If you're not very familiar, don't worry too much. I will explain what you need to get out of this. Basically, we're plotting the variation of the width in a very particular sense as a function of the diffraction angle theta. Basically, what you get from this is that the crystallite size is proportional to the inverse of the intercept in this plot. So you can see that we have a very similar crystallite size for the two tetragonal samples, but a much lower crystallite size for the ball mill sample. So in the hundreds of nanometers for the tetragonal samples and down to about 25 nanometers for the ball mill one. And the gradient here is actually proportional to the microstrain. So that is the average deviation between the size, the lattice volume of crystallites, of different crystallites in the material. So again, we see an increased microstrain for the ball mill material as compared to the tetragonal sample. So to summarize, ball milling in Na3PS4 leads to decreased crystallite size, increased microstrain, and a compressive macrostrain, so a decreased lattice volume. So all these effects can be thought of as coming from the mechanical nature of mechanochemistry, that is, the synthesis of materials through the application of constant mechanical force and pressure. So we got the idea that maybe we can explain why mechanochemistry stabilizes the cubic structure by doing some DFT calculations as a function of pressure. So this is what I'm showing here. Basically, we scan at different pressure values and calculate the energy and the volume for the tetragonal and the cubic polymorphs of Na3PS4. What we can see right away on the left is the lattice parameters of the tetragonal polymorph, which have the expectable difference at zero pressure. But as we increase pressure, they converge. When A equals C, we basically have a cube. And we can also calculate the enthalpy of formation of the two polymorphs. I'm plotting here in purple the difference between the enthalpy of formation of the tetragonal and the cubic samples. You can see at zero pressure, the value is negative, so the tetragonal polymorph is favored. But as we increase pressure, this difference, or the absolute difference, decreases to the point where at 15 gigapascal, we get something very close to zero. So basically, we have stabilized the cubic polymorph through pressure. So we can say that we can understand the effect of mechanochemistry on stabilizing the beta polymorph through its the aspect of applying pressure to the material. So we say it's cubic, but let's have a closer look at the diffractogram I showed you just before. The main peaks are indeed indexed in the cubic polymorph, but if we look at the fit of this intense diffraction peaks, we can see very broad reflections that are actually unindexed by the cubic polymorph, and which are actually indexed by the tetragonal polymorph. So this gives us some clue as to, it's not very clear whether this comes from a secondary phase of tetragonal symmetry, or if this somehow a superstructure attributable to the main phase, but we have some sort of clue. So basically what we can do from here is try and investigate more locally what the structure looks like by taking a diffractogram like this and performing a Fourier transform to bring it from Q space, inverse space, into real space. So this is what's called the pair distribution function, as shown here. So we have a real distance on the x-axis, and each peak here basically corresponds to the distance between two different atoms in the material. So we try to fit to the cubic model in agreement with the Bragg interpretation. And you can see that we get something close, but there's still some residual difference. But on the other hand, if we actually try and fit with the PDF with a tetragonal model, we get a much better fit, or a significantly better fit at any point, indicating that actually locally, even though the Bragg diffraction tells you it's cubic, locally, the structure can be better described by the tetragonal model. And I should highlight that this whole train of thought was developed before from the group of Gießen, Krauskopf et al. And I'm simply validating that result here through my data. We went further to characterize a local structure by Raman spectroscopy. So you can see here the Raman spectra of the 3 Na3PS4 samples. From a first look, they're quite similar. The peaks that you see are more or less the same. Basically, they're dominated, the spectra are dominated by the normal modes of the PS4 tetrahedron, noted here in Ni1 to Ni4, asymmetric and symmetric bending and stretching. So then the question was, okay, would we see a difference if the ball mill sample in blue was actually cubic? So we performed some group theory analysis and some DFT calculations, which you can see down here. And you can see basically that all the samples agree much better with the tetragonal model than the cubic model. And if you're curious a bit, the reason for that is basically that in the cubic model, the PS4 in the crystal structure actually enjoys the same tetrahedral symmetry as the free ion. So in that sense, there should be no splitting of the peaks. You should simply have 4 singlet for the normal modes. Whereas in the tetragonal space group, the symmetry, the side symmetry and the unit cell symmetry of the PS4 anion are in the crystal structure are lower than the free anion. So that's why you get the splitting of these 2 peaks. Here, 3 here, 4 here. So basically, PDF and Raman both tell us that there's no critical difference in local structure between the mechanochemically synthesized sample and the solid state sample. They're both equally tetragonal. And the effects of mechanochemical synthesis can be somehow understood in terms of applied pressure. So we have a stabilization of the cubic average structure. We have increased microstrain, reduced particle size, and we have some compressive macrostrain, that is a lower average lattice volume upon mechanochemical synthesis. So since something is happening in terms of pressure, the next somehow logical step was, how can we link the conductivity difference that we observe to pressure? And somehow the most obvious thing I could think of is, okay, let's try and measure conductivity as a function of pressure, which is what we do here. We bring basically our impedance setup inside of a uniaxial press, and we measure conductivity as we apply pressure to the material. So the impedance spectra that we get looks something like this. I'm showing here the spectra as a function of pressure from the left to the right, increasing pressure and increasing impedance. So basically, the conductivity decreases as we apply pressure. This is for the ball mill sample, but we get something very similar for the solid state synthesized sample. But these are not very usual measurements, I understand. So let me very quickly try and capture the essence of what are we measuring here. So I will try to explain this through this simple energy diagram of an ion hopping from one stable lattice site to the next through a high energy bottleneck, the difference between the two being the activation energy. So in order to measure the activation energy, we do commonly experiments as a function of temperature. We plot them like this in Arrhenius coordinates, and the gradient is then the activation energy. Basically what we're doing, if you think about it, is by changing the temperature, we're changing the average available energy that we give to the lattice ion for a hop. And we can think of it in the same way for pressure. We can plot the variation of conductivity as a function of pressure. Again, we have a straight line. From the slope of that, we can get another activation parameter, which ends up being in units of volume. So we call it the activation volume. And what the activation volume basically tells you is, or by varying the pressure, what you actually do is you actually change the average work, the mechanical work that is needed to be done in order for the ion to enter the bottleneck. So you're basically playing with the energy level of the bottleneck up here. So I'm talking about volumes and work, but what does it actually physically mean? You see here a representation of the actual situation in Na3PS4. And the key somehow to understanding what I mean by work is to remember that when we call what we call an activation energy is more rigorously defined as an activation enthalpy. And as an enthalpy, it has an energy component and a mechanical work component. So the activation volume is nothing else but this volume component here, and it describes basically the mechanical work contribution to the activation energy. As the ion, the blue ion here, tries to go into the very tight bottleneck, there will need to be a local expansion of the lattice to allow for the ion hop. And this is just, this local expansion can be understood as the activation volume. And to link with the picture before, basically what's going to happen is as I apply pressure, this is going to increase the energy, the activation energy that I need to overcome in order to get into the transition site and complete the hop. So if we plot our data as I showed before, you get the straight lines that I described, and you can derive from the gradients the activation volumes. You see very quickly that there is quite a large difference in activation volume between the solid state synthesized sample and the mechanochemically synthesized sample. In order to understand this difference, you can conceive of the activation volume as the difference between the needed volume for ion migration and the volume that is already available in the crystal structure. So if I remind you that for the ball mill sample, we have high microstrain and a compressive macro strain. So a lower lattice volume, lower available volume for conduction, you can understand that this can be directly linked to that. So lower available volume leads to a higher activation volume. Basically, the local expansion of the lattice will need to be higher for ions to move in the ball mill sample. If you look carefully, however, on the scale on this graph, you will see that both samples actually conduct very closely to each other in terms of the value of the conductivity. They're both in 10 to the minus 4 Siemens per centimeter, which is a bit contrasted to what I was talking about before about an order of magnitude difference between them. So was I lying? Not really. Let me just plot the same data here with an expanded Y scale. And I can show like this the initial points of conductivity measured in the same setup, but before we apply any pressure to materials. And you will see quite a big difference deviating from that straight line of the activation volume. So basically what we see is that for both samples, we have an increase in ionic conductivity upon the initial pressing, which in the case of the solid state sample is most pronounced, and it actually amounts to about an order of magnitude, which is somehow the same effect that has been previously ascribed to ball milling. So in other words, the effect of ball milling to increase the ionic conductivity of Na3PS4 is somehow equivalent to applying a minute amount of pressure to an ATPS4 and measuring in situ. So just to generalize a bit, basically what we observe when we apply pressure is two different kinds of effects. One at zero applied pressure or close to that is what I would describe as extrinsic, in the sense that it has to do with the structure of the macroscopic object that you're measuring, your pellet. And these effects can probably be linked to some densification or consolidation effects of the macroscopic object. And then we have the intrinsic effects upon applying pressure, which correlates to the story of activation volume that I talked about before. So what comes out of this is that when we actually, and most of the studies that report conductivities at zero applied pressure, we need to be very careful about how we make the sample, in this case a pellet, and how we report the results. And also, perhaps measuring under pressure here and extrapolating the value at zero pressure might be a more reliable and reproducible way to compare the work between labs. So just to summarize our current understanding of the ball milling material, to finish with this part, basically Bragg diffraction tells us we have a cubic average structure, which is different from what per distribution function tells us that we have a tetragonal local structure, Raman as well. When we measure the conductivity under temperature, we see an order of magnitude difference if we do not apply any pressure, but a similar activation energy. When we measure under pressure, we see the same conductivity as long as we apply some pressure, but a big difference in activation volume. So with that, I will finish on the ball milling, and I would like to go on to what I call here the fundamental point of view. So I'm going back to the series of diffractograms in temperature that I showed in the beginning. Here I'm also adding the cooling part. So we go from room temperature to 550 C and all the way back down. I already talked about the alpha to beta transition, but now I would like to focus on what happens in between, or on at the high temperatures here. So we expected the thing to melt, but like I said, this doesn't look like a melt. We have the appearance of very sharp diffraction peaks. And in conjunction with these diffraction peaks, we see a very distinct increase in, let's say, the background of the measurement, which is not actually a background, but it's diffuse scattering. It's diffraction that is not Bragg diffraction, basically. And the whole effect is reversible on cooling, getting back the beta and the alpha phase. So we conclude that what we see here at high temperature is a new polymorph never before observed that we name gamma, and we'll describe further here. So just to go back and set things straight, this is the same thermogram that I showed in the beginning. Indeed, the mechanical stability of the sample is fine after 500 C. I concur to that. And this is because it's not a melt. We can reproduce this thermogram, and we can go further to actually determine the true melting point of the material. A simple visual test shown here shows that I'm still solid if I heat up to 700 C, and I actually melt. I lose the shape of my initial object. Only if I heat up to 800 C, and through more DSC experiments, we can determine the start of the melting at around 760 C. Now, going back to the structure, the diffractogram at 550 C can be fit very well with an FDDD symmetry and these lattice parameters here. I would like to highlight once again the wavy nature of diffuse scattering shown in both panels here, as well as the rapid diminution of the peak intensity, which is linked to high disorder in the structure, typically modeled with B factors, the bipolar factors. And according to these lattice parameters, this also represents a stepwise about 10% volume expansion upon transition from the beta to the gamma phase. So from having the average symmetry and the size of the cell, we would like to have now a more structural model of how the thing looks in the atomic scale. This was quite challenging, but the key somehow observation was that the electronic density, once Fourier transformed from the diffractogram, points to large similarities with another material that crystallizes in the FDDD symmetry, namely sodium sulfate, shown here. And if we simply take the structure of sodium sulfate, we replace the sulfate by a thiophosphate, and we expand to our observed lattice parameters, we get a very plausible structure that initially has a decent preliminary fit to our peak intensities, let's say. So going from here, basically we only have 2 sodium, we need 3. So what we did is we performed DFT calculations to figure out where the energetically where the sodium would prefer to sit in such a structure. And what we actually found is that there are multiple sites in such a structure where sodium has very similar energies, and actually more sites than we have sodium atoms to fill them with. So we describe this with such a disordered structure of multiple sodium positions partially occupied. So taking now this starting model, what we can do is we can put in temperature and look what happens through molecular dynamic simulations. So this is what I'm showing here. You can admire the distinct mobility of all the atoms in the structure here. While I take a sip. You can see the PS4 tetrahedra performing full rotations irrespective of one another. And you can see the sodium ions in green practically swimming around these rotating tetrahedra with no real stable sites and with distinct mobility. Can show the same thing here as a static picture. Basically what we're doing here is we're just tracing the trajectories of the simulation that you just saw. On the left, we have the sodium moving around in green, again, diffusing very, very freely with no distinct hops between distinct lattice sites. And on the right, you can see the phosphorus and the sulfur trajectories. And you can notice that the PS4 as a unit stays translationally fixed, but the sulfur is very free to rotate around the central phosphorus, doing basically free rotations around the phosphorus. So from the molecular dynamics, we can also extract the diffusivity of the sodium ions, shown here on the left through the blue stars, which has a very low activation energy and distinctly higher diffusivity than all the previous simulations in the literature of the beta structure. And this conclusion is also consistent with what we measured experimentally through impedance spectroscopy. You can see on the right. As we heat up to about 500 C, we get a stepwise increase in conductivity, a flattening of the activation energy. I would like to note here the values, right? So this is close to 1 Siemens per centimeter. And the whole effect is reversible upon cooling. So the last data that I would like to show today is the corresponding pair distribution functions as a function of temperature. You can see here. And I would like to quickly highlight what happens upon the beta to gamma transition right about 450, 500 C here. Basically, what we see is a complete flattening of the pair distribution function after 4 angstrom. The only 3 peaks that are conserved are the ones linked with the first neighbor interactions, so the PS, the SS, which make up the PS4 anion, and a sodium sulfur distance around 3 angstrom. So this is quite weird in the sense that this flat PDF corresponds to the very sharp Bragg reflections that I showed just before. So it's quite unintuitive and it took me a while to understand, but a key way to somehow convince you and me that this is not an artifact of something, is we can take the molecular dynamic simulations that I showed you before, and we can extract the pair distribution functions, the corresponding pair distribution function from the simulation. You can see we get a perfect agreement. In fact, we have only the first three sharp peaks shown on the bottom for PS, SS, and NAS. And the rest of the, let's say, higher distance peaks are quite flattened. And this can actually be linked to the fact that there's no short range correlations in the material. In other words, one sodium is not limited by what another sodium is doing. One PS4 rotating does not have to match the next one rotating. So everything is moving somehow in a liquid-like sense without regard for what its neighbor is doing. So we have long-range symmetry from Bragg diffraction, but no local correlation apart from the first-order covalent bonds through PDF. So to summarize this part, are we dealing with what we call a mesophase? A mesophase is something between a traditional liquid and a traditional solid. We have here a latent heat of transition that is quite high, of the order of melting, more than a phase transition. We have a large volume expansion. We have the combination of Bragg reflections and liquid-like diffuse scattering, a vastly increased conductivity and reduced activation energy. And the most direct proof of all is the molecular dynamics observations. And using all these clues, we propose that gamma Na3PS4 is basically what we call a plastic crystal. So it's a mesophasic material that is macroscopically solid, remember, mechanically stable, keeps its shape, but is locally liquid. The ions within it move without any sense of what the next ion is doing. So summarizing here, we have reevaluated the melting point of Na3PS4. We have discovered a new polymorph for Na3PS4 called gamma at high temperature, which we ascribe to plastic crystalline mesophasic character. A sort of question open to discussion that I pose here is that this FDDD space group that we observe is quite unique. Most of the other phases in the literature that show similar characteristics, rotational disorder, and so on, actually crystallize in maximal cubic symmetry, FM3 bar. So what is the deal with FDDD is an open question that I would love to discuss with the jury if they're interested. And I would also like to highlight that a very recently paper came out where they basically take our study, they perform classical molecular dynamics on gamma Na3PS4, and they basically confirm and build upon our picture. I thought I would highlight it at the end because I think it's somehow, I'm very proud of someone actually being so soon building on something I came up with. So to finish up, I obviously didn't have the time to talk about everything I've done in 4 years, so I'm just highlighting here the perspectives that I've added in my thesis manuscript. I've done a bit of proof of concept work on the aqueous synthesis of sulfide electrolytes. I've looked more generally on the high temperature behavior of compounds made by tetrahedral ions to compare them to one another. And I've also applied more or less similar methodology that I showed here for Na3PS4 to the lithium analog Li3PS4. So I think I'm on time to finish up, yes. I would like to finish by just a big thank you to all the different families of people, the different networks that I've been part to, and I'm very glad to have made so many acquaintances and many collaborations, the Alistor, the French RS2E network, and the German Academic Exchange Service. Also all the people I've worked with and interacted with in all the different labs I've been hosted in, as long as the supervisors, as well as the large-scale facilities that have accepted my proposals, and all the beamline scientists that have been there to help me learn about such methods. And I think I'm good. Yes.
Okay, so thanks, Theo. You have done in the right time, 35 minutes, which is perfect. Very nice presentation, very well explained and all the details and so on. So I think, we are going to start by the questions, and I am going to give the floor with the first reporter, which is Mark Wagemaker, which is first going to ask you a few questions.
Good morning, Theo. Can you hear me?
Yes, very well.
Great. Well, I'm delighted to be part of the commission, and I was really happy to see your presentation, and also, yeah, I was really with a lot of pleasure reading your thesis, and I must admit there's much more interesting results that I can comprehend in a few reads, but I'm in the lucky situation that I can ask you many questions also in the future. But obviously, there also in this moment, I have some questions. Maybe starting with the structure determination of the sodium 3PS4 for your discovered gamma phase. So already from all your efforts, it shows it's a very challenging structure refinement. And you play a number of tricks, but you actually use a single PS4 configuration. But then I think if I understand correctly, you use several sulfur positions, and that allows you to have several anisotropic displacements parameters to kind of capture the sulfur mobility. So far, is that correctly understood?
Yes, sir.
Okay. So I was wondering, it's more like interested in how you approach this thing, but did you also try to lower the symmetry of the structure in which you refined it, which gives you much more freedom also in your ADPs and your anisotropic displacement parameters?
To lower the symmetry.
Yeah, the lower the symmetry of the structure that you fit in. Of course, the ADPs are kind of are restricted by the symmetry that you refine in, obviously. So by allowing, let's say, a lower symmetry, that also gives more freedom in your ADPs. And I was just wondering from an approach, how you approach this kind of problems, whether you tried something like that. Maybe it's not feasible. It's just
So, I mean, in any case, a lower symmetry, okay, let's start by this. FDDD is somehow the highest symmetry you can have for an orthorhombic space group. So any orthorhombic space group with lower symmetry would have more diffraction peaks that we really do not see. In fact, the FDDD space group fits perfectly all of the observed peaks, even down to very high Q. So in that sense, I mean, I tried a couple of space groups that were close to FDDD. So, for example, F222. But if you Fourier transform the electron density of that, it gives you something nonsensical. So I quickly abandoned looking for another space group because basically it would not be exactly supported by the data. I mean, obviously you can always have Bragg peaks with zero intensity, right? But I did not actually try to fit something with lower symmetry. And I do not quite understand your point on how that would improve the fit somehow.
No, I'm just
facilitated.
The interesting aspect of your structure is the difference between local and global order, right? That's the whole, and that's immediately the challenge in your refinement. So I was wondering, and so you can lower the symmetry, and of course that means if your lattice parameters remain the same, then that still obeys, let's say, the reflections of a higher symmetry, but in terms of a ADP, it kind of allows you to break the local symmetry. If you see what I mean.
I see the point. Yeah. So basically, you're proposing we do something similar to what we did on the PDF of the alpha and the beta phase. Basically, trying to get something that appears to be more symmetric with the. No, I did not perform such a thing.
Okay, I was just curious. I'm not saying it will work, but I was just curious whether this is an approach you considered. Thanks, very clear. So then I was interested. There's a let's say a big unknown that you didn't discuss, although you also, it's clearly also in your results, and it's about defects. Let's say in sodium 3PS4. You mentioned them, I think, for instance, at the conclusions of chapter 5, say they may play a role in stabilizing the polymorph and enhancing the ionic
Right.
No, I need to, somebody is trying to call me. I need to off, sorry.
Yes, so let me go back to, if I can, somehow, to a slide of my presentation to answer that question. So basically, after the work of Hayashi that showed that the mechanochemistry increases ionic conductivity, he proposed that it's because we stabilize the beta. But what I didn't mention is that this interpretation has been challenged by many groups, both on the experimental level, by producing tetragonal samples that conduct very highly, and also on the computational grounds, basically people simulating the tetragonal and the, I think a series of this publication came from your group, so you know very well that if you simulate the diffusion coefficient in the cubic and the tetragonal phase, they're very similar. And in fact, what has been proposed is that what mechanochemistry does instead is it actually introduces mobile defects into the material. So it has nothing to do with the average structure. It just has to do with a higher density of mobile defects. And this has somehow been I would say the leading argument, the leading hypothesis about why mechanochemistry increases conductivity in these materials and others.
Yeah. Okay.
But what I should say is that, well, first of all, we see from our results that I showed that you can actually get the mechanochemical synthesized and solid state synthesized material to conduct very closely by applying pressure. But you are right that indeed, even if we look at my results here, in the end, the ball mill sample still has the edge, still conducts what, let's say, 2 times better, right? With this data, I cannot exactly somehow exclude the possibility that there is an effect of adding defects. I can just say that it's not the full story. And the thing with defects and mobile defects is it's a nice somehow hand-wavy argument that we like to make in the field, let's say, but it's very hard to actually quantify them, right? So unless you can actually tell me the number, how many defects you have versus how many are in the ground state material, I don't know. For me, I'm still a bit itchy, you know, to get a bit to the bottom of this. So one idea for the future would be to actually develop such methods to actually be able to quantify really what is my concentration of mobile defects. And it's one of the ideas I hope I will work in the future.
Yeah, what maybe I can say. Yes, this is a good idea because, you know, you take in semiconductors. In semiconductors, we know really the amount of doping, amount of defects. So why we cannot do it in solid state material?
Exactly. I actually, while I brainstorm about this idea, is exactly where I looked into semiconductors. So in semiconductors, they typically do these Hall effect measurements, where they introduce a magnetic field to actually steer the electrons or holes in that case. And by the amount of steering, they can actually figure out their concentration and their mobility separately, right? So we're not measuring total conductivity, we're measuring the components of conductivity. I think an idea for maybe for the future would be to develop an analogous ionic Hall effect measurements. And actually some people have tried that in the past. The problem is you need either basically the ions move much slower than electrons or holes. So in order to see something in such a measurement, you need huge magnetic fields or high temperature, basically. So the only such studies I've seen were either were made on molten salts or really high temperature for solid electrolytes. But there hasn't been any such interest as of late, like in the last push, let's say the 10, 15 years. So I think with better equipment and better knowledge, maybe we can actually do something.
Can I quickly jump in here? You can measure defect concentrations in ionics. This is done in Syria, for instance, via dilatometry. It's just in these diaphosphates, it's really difficult to make a very dense bar-shaped sample, like 100% dense, and put that in a dilatometer. But in principle, this is doable. The oxide ion conductor field has done this over decades.
I'm not very familiar, honestly, with this. So I don't know if this is the time to actually discuss it, but I'd be very, very interested to hear about this.
But Theo, I'm also a strong believer that diffraction can even dig up some details. But what if you would cool these materials down to very low temperatures and measure the occupancies more accurately? That's
yeah. So basically, you're using diffraction as for compositional analysis somehow.
Yeah,
this is one idea, but I think, this is one idea, but I think if we really want to try and measure the composition, really, there are much more accurate and I guess more straightforward analytical techniques. I mean, you can measure how much sodium is actually in your Na3PS4 sample through titration, through ICP, and so on.
But I would say that's tricky if you have some glassy fractions, and yeah, that sounds very tricky to me.
Yeah, it's true. It's true. And I guess we need to remember that what we're actually looking for is not necessarily the total sodium or lithium content, is actually the mobile sodium or lithium content, which further complicates this idea.
Yeah, so you actually, it's a combination of that. You would like to know the number of defects, but in particular also the number of mobile species compared to the less mobile ones. Yeah. Yes, relating to yeah, this maybe also relates a bit what I was thinking on your activation volume. So at first, to me, it was a bit surprised that your ball milled cubic phase has a larger activation volume. I guess that's immediately also seen by the smaller lattice volume of the material. So then you would expect actually that the conductivity would be worse, right? It has to make more volume, but again, interestingly, leads to this local effects, like the ability to locally create volume for the diffusion. And this is a bit also why I thought maybe defects could be.
Yeah, indeed. So, like you say, I guess intuitively, as much as anything can be intuitive,
Yes.
the larger activation volume should impede ion conduction if everything else remains the same.
Yeah, so
I guess yeah, that's another point why we cannot yet exclude other effects acting on ball milling, because otherwise we cannot explain why still we conduct at the same level, or that still the mechanochemical sample has an edge. But the other thing I would like to highlight based on your question is that the activation volume in principle only acts or only increases the activation energy in the presence of an applied pressure. So in order for it to actually have an effect at zero applied pressure, let's say, you would need to postulate some sort of residual strain on the material, which is not out of the question, but just a key small point there.
Yeah, but it's basically what you're saying, right? That because of the mechanical synthesis, your phase is under strain. So okay, but then in your relationship for your activation volume is obviously the compressibility, which you nicely demonstrate.
Yeah, I haven't shown it here, but I can go to my thesis for
No, it's okay. I've seen it, but I was thinking that's obviously that's very clear. But then I was also wondering, but this local effect of creating volume sounds like, again, that there's also more to it. What creates the locally the activating volume? It's like I don't know. For instance, if the bonds are more polarizable, it's easier, to open up the window, right?
Yeah. So
then it comes like, there's phonons, there's this compressibility. So how should I merge these views, or is the description of the activation volume not yet complete, or am I just mixing up?
I wouldn't. Basically, all this work that I've based my measurements on was done mostly in the 70s and 80s, so more fundamentally minded studies rather than trying to develop electrolytes for solid-state batteries. And there has not really been, to my knowledge, any real evolution of the concept since then. But still, apart from what I've shown here, there's another approach to quantify the activation volume, in which they take, in fact, exactly what you mentioned. So you identify the phonon mode that is responsible for moving the sodium ion to the bottleneck, and respectively from taking it away to complete a hop. And basically, the activation volume is then the derivative, the variation of the energy of that mode as you apply pressure. So yes, it's directly related to the dynamics of the material. And I agree that intuitively, again, a softer material should present a lower activation volume, yes.
Okay, thanks, clear. One thing I was also wondering if it's possible to explain is when you when you fit your Bowman cubic sodium 3PS4, then you fit it with sodium on the 24F position, right? Which is like an in-between position, let's say, to what you would think is the equilibrium position and the saddle position towards the next side, right?
Yes, I mean, I tried multiple different positions to explain what is apparent as a sodium disorder, but the one that fits best is indeed 24F.
Yeah. Now I'm not. So I always believe experiments, much less DFT, even the DFT that we do ourselves. But when we do DFT on these cubic structures, and we put the sodium on this 24F side, it just immediately relaxes towards the, what is it, the 6B side.
Oh, yes. Yes.
So,
this is not necessarily surprising in the sense that you can see that the 24F is simply an anisotropic extension, if you will, of the 6B side, right? So what we're explaining here is not necessarily where is the stable position. What we're explaining through such a model is we're capturing basically the mobility of the sodium that is here perpendicular, or not perpendicular, parallel to the axis. Right?
Yeah, to the diffusion pathway. Yeah.
So this is really what you're seeing here, not necessarily the stable position is always going to be the 6B.
Yeah. Okay. Of course, it keeps being intriguing. Your phase transition towards the gamma phase, where you ended up with this local. I thought it was a very nice description of this mesophasic or material, where you show there's actually no correlation how sodium, next door of the next sodium or the PS4 group, that they actually don't hardly see each other anymore, right?
Yeah.
So, that's super intriguing. And wouldn't phonons also be like a way to study this? Because phonons are that's the collaborative motion of this unit. So it actually requires that they see each other. So it must have a drastic impact on it.
Well, I think you might have noticed in my manuscript that we actually performed inelastic neutron scattering exactly with this idea in mind, try and see the contribution of phonons to this phase, and I can pull it up, I guess, quickly, more or less. But what you actually see is that similar to the PDF, the phonon spectra simply flatten out. You actually cannot see any.
Yeah.
Right. Yeah. Here.
Yeah.
So you can see as soon as you go to the gamma phase, you basically have no features. We're doing a molecular dynamic simulation, so to try and extract from there somehow any phonon type correlations to plot basically something like this, a density of states that might be a bit more insightful than this potato here. But at the moment, I have no real answer that I can put weight behind, let's say.
No, but this is very clear. So then maybe as for now, final question, if I'm allowed still, then so that was a lot about the sodium, intriguing sodium 3PS4. Now a bit back to the general challenges of solid state batteries, and maybe it's not a surprise to ask about stability window. So I think it's the end of page 55 in your thesis, starting also on page 56. You describe the thermodynamic stability, which is basically comparing the free energy of your solid electrolyte with your decomposition products, and thereby you can construct an electrochemical stability window. And you mentioned there, and it's kind of intriguing. It's defined. That you can in practice extend that beyond the thermodynamic limit. You see that it's an overpotential that is required, and underneath that is you write the rearrangement associated with the decomposition, and that is linked to the charged species in the electrolyte.
Yes.
Yeah. So I was wondering. It's rearrangement associated with decomposition, but also the link with the charged species. So, all the species are charged, but I guess you mean the lithium or the sodium, the charge carrying species.
Yes.
Am I right? Yeah. Okay. So it's a dynamic effect. So it's basically a transport-related effect then basically a resistance that induces overpotential. So far, did I follow it correctly?
Yes.
Okay. So, but that would mean that if I lower the current, let's say this additional stability on top of the thermodynamic stability would be lower, right?
Yes.
Okay. So, but then I'm a bit confused because for decomposition, I need more than just taking out or putting in and moving lithium or sodium. It's like I need to change the host structure. I have to decompose the structure. So could you help me out here?
Well, basically, again, there's a lot of effects that can come into play, and you described two of the main ones, right? So for the rearrangement of the structure, you are going to need to have a certain diffusivity, let's say, of each component. You might need to also break and create bonds, so the energetics of that and the kinetics of that, and then the mobility of the species, because typically such interfacial reactions that we're discussing there have to do with separating a phase into a lithium-rich or sodium-rich and a lithium-poor part under the effect of the applied current. But beyond that, I'm not sure exactly what is your objection or your confusion. What is the contrast that you?
Now you basically say that the overpotential you typically see if you try to measure the stability window, you typically measure a overpotential as you described, right? And I'm questioning whether that's kinetic or not kinetic. So actually thermodynamic. But it's
I think by definition, when you say over potential, it's kinetic, right? Like over potential is the potential beyond the thermodynamic potential.
Absolutely, completely agree. So my question goes then. So I should rephrase. How can you be sure that it is an over potential? Obviously by changing the conductivity, and did you see people doing that then, and what happened? Because that is indeed.
You can do something super slowly.
Yeah, exactly. But that's what people try, right? I mean,
yeah. I mean, you can see a typical example of that is the early cyclic voltammetry results that would tell you that LGPS is stable up to 10 volts or whatever.
Exactly.
But then if you measure at an actual slow speed and take a few hours or days for the measurement, you will see very clearly the peak of decomposition.
Yes. Yeah. Yeah. So what if just hypothetical? Actually, it's not so hypothetical. But let's say that you do this and you have it extremely slow, but you still see that the potential is the voltage window is larger than you would expect thermodynamically. So what would your do?
Well, when you say I expect thermodynamically, is based on what? Is based on calculations or what?
No, what I really see. So we have, let's say, in the definition, the thermodynamic stability window, which is the difference in formation energies, basically, between.
Right, but this you can only really quantify, as far as I'm concerned, computationally. No, I mean, in the end, the experiments are going to get you closer and closer to the real value as you go slower and slower. But obviously, there is a limit to how slow you can go.
After that, but you say if I go infinitely slow, I will approach this limit that they calculate.
No.
Yes.
Oh, no, okay, that's good. Then we have plenty of this to discuss in the future. I will leave it here. Yeah. Thanks.
Yep. Okay, I guess you finished, Mark. Thank you very much.
Yeah.
Now I'm going to give the floor to my neighbor, one who's really ask you a question now.
Okay, thanks very much, Jean-Marie. So today I'm not your neighbor because I'm at home. So thanks very much, Theo, for the nice works and nice presentation. And thanks a lot, Christian and Saiful, for inviting me, being part of the jury. I really enjoyed the presentation and also reading the PhD thesis. I think it's you could obtain important results for the community, and this is really a nice one. Still, I think I was a little bit annoyed in some point of the PhD thesis, in the way that you choose to do PhD on papers.
Yep.
And the translation of this is that we have 3 chapters, which are 3 papers, and chapter 4 and 6 are really extremely closely related, while chapter 5 is slightly different. This is the one with the mechanical synthesis and pressure things. So this creates some redundancies. We see, for example, the synchrotron experiment for the gamma phase is presented 3 times. Same for the Raman spectroscopy and the DSC plot as well. So also some tables are shown several times, some explanations are given several times. So this I detailed in my written report. I think it wouldn't have been such a huge work to try to compile these 2 papers into one and make one single chapter out of this. I mean, I think this is a pity, because I mean, we have the feeling when we read that to see things a first time, sometimes they are just shown. For example, if I discuss, for example, with synchrotrons, sometimes they are shown for the first time in 2 theta angles, and later they are plotted in Q. So I guess this is the same experiment, but it's not clearly said. And same for the Raman spectroscopy. When it's presented first, it's not fully interpreted in terms of symmetry analysis, and this comes maybe 60 pages later in chapter 6. So this is kind of pity. But I understand that you made this choice on doing this PhD and papers. So, and I see that in the oral presentation, I mean, you choose to combine everything, and this much better, I think, for this part, having something more constructed. My questions will more focus on the fundamental part, especially on the high temperature gamma polymorph, because I mean this is really a really important result that also raises many questions. So let's first start with some technical questions about how you solve the phase. First, maybe a small comment is that, as I said before, it would have been nice to see a table of lattice parameters and atomic position in the PhD.
Okay.
Chapter 4 is devoted, the main result is resolution of this gamma phase, but actually the first time we read about lattice parameters is in chapter 6, so really at the long after having seen the refinement, and we have no table, so it's very nice that you provided the CIF files, but so CIF files, I think it's really nice to provide, but it's complementary, and of course, I mean, it would have been nice to have both. So, for example, I mean, when you open the CIF files and when we read what the strategy you choose to solve the gamma phase, we see that you end up with 29 sodium positions. I think all general positions, so 3 parameters X, Y, Z, and they are all partially occupied with a very, very small occupancy factor, such as, let's say, 10% or something like this. And this is all different, all occupancy factors are different, and from the CIF file, the standard deviations are not provided. So actually, we have no idea of what was refined, what were the constraints you put in the refinement. If I sum all occupancy, I see that you get the right stoichiometry, so I get you put this as a constraint. But I have no idea if you would refine all parameters at the same time. I mean, it gives a huge number of refined parameters. Is it still plausible regarding the number of reflections, regarding that you only have powder data? So you have limitations. I mean, you probably need several reflections to refine one parameter. So can you comment about this? I mean, being in pulse minima, strategy, constraints, spots, and so on.
Yes. So a lot of things to say. One, I will start by saying, first of all, that this refinement was definitely a bit beyond me. This was done in collaboration with Professor Oliver Clemens in, now she's in Stuttgart, professor in Stuttgart, who also had access to Topaz, which I did not have, where you can do a lot of these associations and combined limits, restrictions to do complicated fits in any case, that are quite a lot harder to do with the free software like Foolproof, Fiana, and so on. Anyway, indeed, we can fit all parameters in the end at the same time. Indeed, this is a bit of an overextension compared to the amount of peaks that we have. The reason why, in general, I did not want to put too much weight behind this Rietveld solution is exactly because I don't think that, with no offense to anyone, I don't think that Bragg diffraction is a method that is particularly suited to describe such a structure. I mean, if you just look here, the solution that actually shows very well, very good agreement between the data and the calculation, we have this practically, I don't want to say nonsensical, but what does it actually tell you? These are ellipsoids at 50% occupation. So imagine if I put them at a 90, that is normal, right, to present such things. And the sodium atoms, yes, there's a lot of positions, but it's actually because, as seen in the molecular dynamics, the sodium is everywhere. There's, if you look at the Fourier transform electronic density, there's really no sign of any really stable atomic position anywhere. So this is just a way to smear basically electronic density everywhere that is not a PS4, basically. I hope I'm capturing some point. Maybe you want to direct me more to what else you might be interested in.
Yeah, well, I mean, thanks for the explanation. I mean, indeed, for me, I mean, it looks like it's over, I would say, over refined. Same, I mean, going back to the question of the previous reviewer, I mean, having two sulfur with exactly the same position, but different BA and ISO, then, I mean, obviously there is a problem because BA and ISO, they should be able to capture the motion. Yes, I mean, if you, or it means, would it be a sign, for example, that actually the symmetry is not FDDD, but FDD2, as was suggested by Superflip or something like this? Because it should, something is, it's very unusual to have two sulfur at the same position and refining independently anisotropically. And then we have this question of this sulfur, you put a 3/4 occupancy or 1/3 occupancy, 2/3 occupancy. I have no idea what is the impact of this, what is the meaning, physical meaning of this occupancy on the refinement. So I understand that the refinements were fine. Oh, by the way, I mean, you can do with foolproof complex.
I mean, I've reproduced it with foolproof, but I don't think I could really code foolproof to do the complicated things that we needed to do here. Sorry to interrupt.
No problem. So maybe I'll move to another question slowly. So this structure solution, I mean, you explained nicely that you found it by analogy with Na2SO4. And I was wondering then, why didn't you try to reconstruct it from the alpha and beta polymorph? Because you nicely show the relation in chapter 6 between the alpha and beta polymorph with the sodium that are slightly moved, the PS4 that are slightly tilted. But actually, this is obvious when we see tetragonal cubic. So obviously there is a group-subgroup relation, and this, even when you look at the patterns, it's completely obvious. Here, of course, I mean, can you find some crystallographic links between the gamma phase and the beta phase?
Yes. Let me just quickly go back to I will answer this question, but you raised some good points on this refinement. I would like to clarify them. I guess that's the point of this process. Just so the 1/3, 2/3 occupancy is simply fitted. I do not try to find any physical explanation for this. You mentioned that the anisotropic displacement parameters should be able to capture the motion. I do not agree with this necessarily. I mean, the Debye-Waller factors, they were designed to indeed to describe harmonic phonon-like behavior, right? But if you look, and in connection with what I answered to Marnix before, if you look at the molecular dynamics and you look at the inelastic neutron spectra, you cannot really say that these material or these PS4s engage in what we would call classical phononic behavior, right, in a solid. So in that sense, I think it's more of a limitation of the Debye-Waller formalism rather than, let's say, an error in using it here or something doesn't make sense. I would be surprised if it did make sense, to be honest. And then there are other things you can do. For example, fit anharmonic displacement parameters to try and capture such motion, which I'm playing with. I don't have something to show yet, but there are ways to extend to extend that. with regards to how can we, if we can derive the gamma phase from the beta phase, the short answer is no. The short answer, there is no crystallographic group-subgroup relationship between the gamma phase and the beta phase, so FDDD and 9,4/3M. This was actually somehow maybe not a criticism, but it was highlighted by a recent paper looking exactly at the relationships from the crystallographic point of view between the polymers of Na3PS4. So it's, but it doesn't need to be, right? It's a first order transition. We described this in the last chapter of the main results. It's a first order reconstructive phase transition. So it involves a high latent heat that completely basically disregards symmetry relations between the two phases. I hope that's...
Well, yeah, this is still pretty unusual. I mean, going back to this, because I think that the main point indeed is why is the symmetry so low at high temperature? I mean, naively, we would expect that this is what is seen in so many phases, and this is Curie principles and so on. When you increase temperature, you go to higher symmetry. When you increase disorder, you go to higher symmetry. And if you have some rotating PS4 or sodium moving everywhere, you expect to end up with a small cubic cell, as was reported in so many compounds. So here, this is, I have two things that are strange. I mean, FDDD is pretty low in symmetry, and the unit cell is pretty large. I mean, you have one lattice parameter, which is 20 angstrom. So I can see that indeed it indexes perfectly. Yeah, this is some work with this. I did, I mean, with rotational disorder of the PS4, what you show. So, and here, crystallographically speaking, you do not observe this at all. So this is really surprising for me.
Right. Yes.
Well, I don't have the answer, but did you check if you have some other compounds where you have a lowering in symmetry when you increase disorder or when you increase temperature? I mean, did you find? Yeah, apart from the analogy with the polymer, the copolymer. I mean, in inorganic field, did you find something?
There is examples of lowering symmetry with increasing temperature, yes, but with no real distinct somehow connection with what we see here. I mean, the lowering in symmetry is one aspect, but all the other weirdness that happens should be considered somehow as a whole, I think. And what I've looked for specifically is to try and find any other FDDD phases with rotational disorder. And this I can say that I have not found. And it's for this reason, really, I mean, this slide highlights exactly this, that every material that I know that is made, that is characterized by rotational disorder of the tetrahedral ion or even such a cage-like ion, they all go to FM3/M, like you commented. So to the best of my knowledge, right, it's the only one that shows such a behavior. And this is why in the last chapter I had to expand, let's say, my search to more than just inorganic crystals, and I made this analogy with the copolymers. So
I personally think that FDDD, I'm not sure to answer this question. I mean, we need to be linked to the FDDD one. It could be another space group, and I don't think that the symmetry itself will have an impact on it. I mean, maybe I'm wrong, but here you choose to solve in FDDD, but as you said, I mean, you probably could solve in some other space groups. Superfleet suggested you FDD2. Maybe if you change the lattice parameters and did some, reconstruction with A, B, and C, you could find another space group. So FDDD, well, I think it's just, I don't think
we
that
did
was,
try.
yeah.
There is no relationship that I could find with anything tetragonal or cubic or any somehow distortion of them. And I mean, it goes back to the same point. Even if I lower further the symmetry, right, we go further into this point of why are we keep doing this? Why do we keep somehow reducing the symmetry, even though we're looking at a very disordered high temperature phase? So it's a bit, the two points are a bit in contrast to each other. But,
maybe I can inject here. Did you figure out what is entropy configuration energy? You calculate entropy configuration energy. And how this stuff change from different type of symmetry?
How would I do that?
More or less, when you make a compound, you can nearly look at this order and calculate this entropy. These people are doing it.
Experimentally, you mean? Or,
no, by calculation.
By calculation, no. We have, I mean, we can get an idea of the change in entropy upon phase transition by using the latent heat that we see, and by assuming that the latent heat is all is equal to basically to the change in entropy over the temperature of transition. I've done this calculation in the last chapter, but not by DFT calculation. No. But you would expect a sizable, indeed, you would expect a sizable such entropy difference between the classical solid beta phases and alpha and beta, and then the gamma phase, for sure. This is another somehow key hallmark of plastic crystal phases.
Yes. Anyway, okay. Go ahead. Sorry.
Yeah. So going back to the gamma phase, so you found it by neutron diffraction. I mean, but I saw that the statistics of the neutron pattern was not good enough, and then later you remeasured it in Polaris in the UK.
Yes.
But I was surprised that you only show a profile fit, yeah, and not a Rietveld fit. So was there some problems doing the Rietveld refinement with neutrons? I mean, why you're showing only a profile matching?
The short answer is I simply didn't do it. The longer answer, I guess, connects back to my comments before on how I think other methods are much better suited to try and understand this phase. My efforts right now are concentrated on rather than small scale Rietveld models, try and build big box models that I can populate with RMC, reverse Monte Carlo simulations, and then using that fit both the pair distribution function and the Bragg diffractogram at the same time. And in that way capture, instead of resorting to the By-Waller factors, which I criticized before, try and actually discretely point to the sodium distribution and the PS4 distribution, captured through averaging through a big box simulation.
Okay, so but still, I mean, well, here I'm not sure I agree fully with you, because I mean, you clearly have Bragg peaks on they should be understood with a crystallographic model.
I mean,
this is my thing. Is there a possibility, for example, that at high temperature you have a slightly change in the sodium content through the formation, for example, of an amorphous phase, and your crystalline phase has a slightly different stoichiometry that would explain that the symmetry is completely different. And when you cool back, then it would reform the Na3PS4. You see what I mean? How can you be sure that in the gamma phase you have exactly this Na3PS4 stoichiometry and not something slightly different in case you have some secondary phase forming, which would not be crystalline? Did you consider this?
I did a lot, actually. I thought I was crazy when I first saw this for like a year. There's a few ways to answer that I've come up with. one very simple one. If you look at these diffractograms, what you're proposing, I guess, is that we have some sort of incongruent melting into two different phases of different stoichiometry, one sodium rich, one sodium poor.
Yeah.
But I'm not sure I've ever seen a phase diagram where you can have incongruent melting and then recombine back to have incongruent or congruent solidification after. So I'm not sure that is possible thermodynamically. If we do make two phases at 550 C, we should see two phases also when we cool back down, from what I understand. I'm not sure if you agree. And I mean, another point to make is that even when we are, so this is in the last chapter, even if we are in the gamma phase, we still see very clear signature of a PS4, damn it, where is it? Of a PS4 anion, a PS4 anion which is charged 3 minus. So that's another sort of way of saying that I need to have 3 sodium to coordinate that. So I cannot really have a structure with PS4s, but not 3 sodium around it, right? And it's zoom in.
Yeah, I see. Because regarding your, maybe I will slightly shift to other questions, because I mean I see that time is running. Just a remark with your going now to chapter 5. I mean, there are different things. I mean, first a comment is that when you create your models trying to fit the ball mill cubic phase, you present different models with different sodium distributions. I think it's page 116, because I see that this is yeah.
On pages.
It's box 8.
No.
Yeah, it's 116. So I think before. Yes, this one exactly. And so here, I mean, I tried to understand this box, but I had some difficulties. So basically, you create different sodium distributions, putting sodium in different sites. First, what I missed is that I don't have the occupancy of those sites. For example, of course, if you put one sodium in 6B for first model and one in 12D, you don't have the same number of sodiums. So probably, I guess that you applied some occupancy factor in it that you didn't mention. Did you?
I mean, I do mention here the number of refined parameters. I'm including whenever there's more than one sodium, I'm including the fact that I am fitting the occupancy.
Yeah. But
I did not put the results indeed.
Yeah. But I mean, for the two first lines, you refine only B-iso, but when the first model, you have sodium in 6B, so 6 sodium in the unit cell, while in the second, you have 12 sodium in the unit cell. So
yes, I mean, it's adjusted. Yes, it's adjusted. It's half occupied in this case and quarter occupied here. Yes.
Yeah. So on here, it's the same when you use 24F and 24G. Maybe for you it's obvious, but for a standard reader like me, we would need what are the X, Y, Z value of the 20F site, for example, because you have an infinity of 20F sites or 20G sites. You need to give the position, I think you need to give the position somewhere. So otherwise, I mean, it's useless. We cannot reproduce.
Okay, you mean the general position as you would get in a table, although, or you mean the result of the?
No, not. For example, the 20F is x 1/2 0, so x should be given.
Okay,
you start
see
with
the result of the simulation. Yeah, okay.
The result or the starting point, because I guess, I hope that when you do some refinements, you start from the hex position, and it will not vary completely through the unit cell. Otherwise, I mean, it means that this parameter has no impact on the refinement.
Yes, I understand. I mean,
you
I can
see what I
hear
mean?
this. Yeah,
And
yeah.
on this, all these refinements, I mean, they were done. I mean, I think it's written just above. They were done using combined neutron and XRD patterns. On
For the
neutron,
result, yes.
yeah, I think it's just above your table S12.
Yeah.
And yeah, exactly here. And you use criteria, which is 1% of X-ray and 99% of neutrons. So basically, you're doing a refinement of the neutron pattern, and you don't care about X-ray pattern.
No, not exactly.
Okay.
The reason why I chose this is because if you look at the actual fit of the diffractograms, for example, basically the He squared factors that I get. Let's see here, for example, for the so the He factors that I get for the X-ray and the neutrons have about that ratio between them. The reason why I get such a big He squared factor, even though the fit is rather decent, has to do more with the small imperfections in the peak shape, mainly at the feet of the peak and the fitting of the background. So the 1% to 99% comes to somehow compensate for this sort of difference here.
Yeah. But I mean, Theo, I think that the high chi-square you have for the X-ray is just because you have a very good statistics. Nothing else.
Yeah, exactly. The error is very small.
Yeah. You should not worry at all about this.
Okay, so maybe we should.
Okay. So I would like. Okay, I was too long apparently. Oh, come on. Let me just congratulate. I would like to congratulate you about the Williamson Hall plot, because this is really a textbook case. I mean, I never got such nice Williamson plot. I see that to get this, you must have something that is completely isotropic in terms of size and strain broadening, which is not the case for the compounds I usually see. So for you, I mean, it's really a textbook case. So I will stop here. Thanks very much again for the great work and nice discussion. I'm sorry for being long.
Oh, no.
Okay, thanks, Gwen. Okay, so now we are going to give the floor to Laurence Croconec from Bordeaux, who is going to follow up.
So good morning, Theo. First of all, thanks a lot to your to your director of thesis, supervisors, it's okay. To your supervisors for giving me the opportunity to be here today and to read your PhD. That is very interesting. I agree with Gwen, very original in the way to give the results, but I would say also very original in the way to discuss the results, and I find it very, very clear, very interesting, and a lot of data and results. I agree with what Gwen said about I would have appreciated much discussion on the parameters you get from your structural analysis, and especially on the bounds and things like that, more or less tables. But it's not the point. I mean, I will not. So I think we see also with all the results you presented that you are really able to challenge a lot of characterization tools in order to get I would say, a lot of insights in complex problems. And so already I congratulate you for that. So I have also questions, and just to come back to the combination of X-ray, neutrons, and PDF, You mentioned that your PS4 were rotating, but you said a lot of times that they were fixed. So in the PDF, I would have expected to find the PP distances to be observed, and I'm not sure it is. It was not clear for me because the colors in your presentation and in the manuscript, because it is diffused there. So I was not sure to really observe the PP distance, and I would have expected it for fixed position of these PS4 units and just rotation around the center.
I agree. I had the same expectation actually, because I kept having this story in my head that we're defining the structure by the position of the PS4. A few ways to answer this. First of all, since there is no cubic symmetry, there is not a single, let's say, first distant neighbor between phosphorus, right? So there is three different distances for the orthorhombic cell. So that means that your one peak that you have in a cube, for example, will get smeared into three. And then the other point, I guess, it seems, I guess, that the phosphorus can move a little bit about its original position. You can see here, for example, again, I don't have a very defined, distinct point where the phosphorus is, but in a general sense, in a macroscopic sense, it doesn't leave. I hope I'm...
Okay, yeah, okay. Yeah, but did you observe, I would say more, I do not remember, larger ADPs for this phosphorus versus other structures in the same systems or in other systems that would explain this disappearance of these phosphorus distances?
ADPs.
Yeah, I mean your BHISO. Are they significantly higher than for this phosphorus here than in other common structure, I would say?
Yes, they're actually crazy huge.
No, but I mean for the phosphorus, huh?
Yes, for the phosphorus. Again, so this is at 50% shown here. So yes, they are huge. Again, that's why, going back to the points by Gwenel, this is why I didn't really put too much weight behind such strict refinement, because I thought, okay, if this is what I get when this is the fit for the phosphorus at 50%.
Yes, okay. Yeah. Yes, sorry.
Yes, yeah, I mean, in that sense, this is consistent with what we get from ritual tests.
Then, considering I would say the NMR results and the problem of defects. In your NMR results, first, considering the sodium NMR, you have observed these two environments. And so from what I remember, you never discussed by itself the link with the structure you proposed for your materials. So you have this 2/3, 1/3 contributions. So from what I see, it's in rather good agreements with what you observed. But is it always the same for all the samples? Do you observe always the same signals, always the same broadening with the same synthesis conditions, and always the same also ratio between these two signals?
Yes, well, I don't know about always. The only NMR results I have are these three that you see here. So, but these three can indeed be fit with the same parameters, the same quadrupole parameters, but changing basically the broadness of the peak. And again, I should also mention that this both the measurements and the fitting were done by Stefan Emge in Cambridge. yeah, and not, let's say, necessarily by me.
Because you mentioned the possibility for defects at the, especially considering the phosphorus NMR, and you mentioned the possibility to have sulfur defects. So more or less, you mentioned about the possibility to have P2S7 entities in your structure. So how do you see this versus the description of your structure? And if you have sulfur defects, it means for charge compensation, you have also other defects. So we come back to the discussion about the stoichiometry of your phase, because it's true that considering that you are doing this phase transition using temperatures, you are considering also phases prepared by ball milling. It is in fact not so obvious to consider that you have exactly the same stoichiometry for all the samples.
Yes, it's definitely a valid point. I mean, with respect to NMR, what we were trying to explain is this sort of side peak that we see here, and the sort of asymmetry of the main peak as well. But again, I propose that this could be due to some sulfur defects, and particularly one that might be somehow favorable to form. Again, I'm talking a bit without any proof here, but from my intuition, would be a connection of two PS4 units into a P2S7 unit, and associated with a sulfur vacancy then.
Yeah, but in that case, considering your structure, you do not have, it means a significant modification of the local structure, because your tetrahedra are...
Yes, I mean, I'm not sure if the fact that I see it in NMR, does that mean that I should really have significant concentrations of them in my bulk? And if then, I mean, I agree that around such a defect, there would be significant modification to the structure, in the sense that it would not contribute then to the Bragg diffraction. It would simply, you would simply have an amorphous background associated with that phase. So the fact that I'm not sure if that's where you were going with it, but the fact that I have no signal from diffraction that points to that is not necessarily to say that they don't exist. You can think
no, I'm not saying that it does not exist. More or less, I would say that I would agree that, personally, I would have expected that your stoichiometry is not exactly Na3PS4. As you discuss in the, I think it is the last chapter for Li3PS4, you discuss about the possibility to have this non-stoichiometry, and probably I would have expected it in this system also. So that's why I'm not saying that this signal is, more or less, I would be convinced by the presence of defect. And to come back also to this defect, when you prepared, because in the chapter, in the thesis, you mentioned these ball mill materials, and you have seen that you had some microstrains of, if I remember, 20% of microstrains for these samples. And the question is, could you play around these ball milling conditions, and could you play around this amount of defects to really perhaps increase also the understanding of this activation volume? Because I agree, for me, it is also not that obvious, the link you made between this activation volumes and this presence of microstrains. So in order to try to get perhaps more insight, it was, the possibility was to try to play for this phase with the amount of these microstrains. So I don't know if it was a possibility, because you did also already a lot of things. So it's a questions to know.
Yes, I mean, it's a distinct possibility. In general, I think such studies are lacking, or at least lacking in depth. I mean, studies varying ball milling parameters. You have a lot of parameters there, but as I comment in my methods chapter, it's very limited theoretical understanding of. I mean, directionally, we know what each parameter does. If I add more balls, if I add more powder, if I increase the milling speed and so on. But this is all still in a theoretical level with no real, somehow, to my knowledge, and definitely not in the field of solid electrolytes, no real correspondence to structure and properties. I mean, it's definitely it's definitely interesting and important for someone to do this. What we've seen so far is mostly such studies from the Japanese groups, where they really are scanning for the optimum somehow in terms of ionic conductivity, and they've been very successful in doing that. But there's no real deep understanding of what about 500 RPM is so special or so on. Mm-hmm. I mean, personally, I do not find it very amusing as a prospect for me to do these experiments, but that does not mean that it's not important and it should not be done. Let's put it that
way. To do the link with the activation volume, I can understand, but to do the link because to do the link with the unique conductivity, it could be it could be interesting to and here it is for the properties as also as solid electrolytes to really because sometimes we have the feeling that even when you are preparing this NaPS4 materials by aqueous synthesis, you do not give the information about all the resolution of the structure for us to be sure that you have exactly the same as the high temperature prepared one. And so, and what intrigued me was especially the unique conductivity measurements, because you said it was in the range 10⁻⁶, 10⁻⁵, but I had the feeling that before it was 10⁻⁵ in the other chapters. So again, I have the feeling that perhaps the composition is not exactly the same. The disorder, the order or disorder is not exactly the same, and the microstrain and so on. So, can you give some comments about these aqueous materials? But it was in the perspective, so I know that you was not able to do a lot of things on these samples, but your feeling.
My feeling, so I have not performed an accurate Rietveld on these materials. The level to which, no, not these, I mean the aqueous ones, not in general. For the aqueous one, it's simply a profile fit that I identify as Na3PS4. Because, I mean, I agree there is the possibility of stoichiometry in Na3PS4, but I do not think that structurally it would be as easy as what I propose for Li3PS4 because of their distinctly different structures. I mean, Li3PS4, I think of it definitely as made from a close packing of the sulfide ions, and then you can fit whatever you want in them. So you can play with the composition of lithium versus phosphorus, and you have a lot of space and a lot of empty sites to do so. If you look at the structure of Na3PS4, there is, at least intuitively, right, there's much less room to play with, right? So if you consider if you consider it as I do, as made up by a body center cube arrangement of the PS4s, then you can see that all of the 6 coordinated sites are actually filled here. There is no real room to put extra sodium. You could make then the argument that maybe I have less sodium.
Yeah, yeah.
But then you would need more phosphorus to make up for the plus charge. Where do you put the phosphorus?
Yeah, or less sulfide, as you mentioned.
Less sulfur, yeah.
As you propose in your NMR that, I mean, I know it was an hypothesis, but it could be also.
Yeah, definitely. If we have off stoichiometry, my feeling would be that it would be on the opposite side than what I proposed for Li3PS4. After that, it is indeed something that comes out from my studies on Li3PS4. Since I also work on Li3PS4, it's applied. It might be applied here, but to my knowledge, there's not something that has been discussed in the literature, an off stoichiometry argument for Li3PS4 like this. Whenever the argument is made that the stoichiometry is changed, it is made in the conjunction of something made on purpose, some structural substitution made on purpose, like the one I showed for tungsten. Right?
And Theo, did you consider by theoretical calculation the possibility of defects in this material?
We have done this, not in the framework of the work that I showed here, but we did consider in a work that we're doing with Piero Canepa the energetics of all the possible defects that you can have in an A3PS4. And indeed, I don't know if it wouldn't be surprising necessarily for an ion conductor, but the sodium vacancies are actually some of the most energetically favorable defects. So that goes along with, it's consistent with the proposition here, yes. Okay. And also the sulfur vacancies as well, I should say, yes.
Okay. So I had a last question concerning, I had others, but I think I have to leave the floor. Concerning the Williamson-Hall plot, I was surprised, in fact, by this very nice plot. And as mentioned by Gwen, because you mentioned in other pages in the manuscripts that you had a microstructure effect. And so I would have expected for some specific orientation, because you can, if it is an isotrope materials, you can plot this plot, consider whatever I would say the crystallographic plane, but for material with a specific microstructure, and you mentioned it in your manuscript, but for me it was not clear from from the figures you gave in your manuscript. And so but I accepted it because you said that you had this microstructure effect. So I accepted it. So here, when I came here to this Williamson-Hall plot, I was a little bit surprised because I would have expected to see this microstructural effect. It means different data depending on the families of the crystallographic planes. And it is not obvious here. So my question here is, how did you determine the broadening of the line to calculate this Williamson-Hall plot?
Yes, so I think there's a few things to clear up here. So when I mentioned microstructure, I don't think that it's necessarily linked to an isotropic strain or an isotropic size. Microstructure can be just simply an isotropic strain and size. No?
You said, I do not remember what it was, that it was obvious considering the figure 1A or something, but I mean, for me, it was not that, it was not obvious considering the figure, but so you observe this considering the line, the diffraction line, so it is associated either to a size or a strain effect, no?
I'm confused, sorry. I'm confused to which point in the argumentation are you referring? Referring to this comparison of the three samples? Or?
No, I mean...
I think I know. You're referring to the discussion around this, or?
Yeah.
Okay, so this is different. So the microstructure analysis I showed before and the Williamson-Hall plot, they come from the fits shown here. So the blue sample, the ball mill sample, is fitted in the cubic space group.
So you get to calculate your Williamson-Hall plot, you consider the profile, calculated profile, in fact.
Yes, that's why it's so nice. Actually, I wanted to answer to Gwen.
Okay.
But it was cut off.
So that's why it's so nice. Okay.
Yeah.
Okay. Sorry, I understand. Sorry to interrupt. Okay.
Because in fact, theoretically, you are supposed to use it's true, the calculated line, but calculated separately. I would say more or less line by line, considering because in order to be able to distinguish between possible strains or size effect, depending on the family of plane or crystallographic planes. So here, if you consider the calculated line, it could be hidden, more or less.
Yes, so I'm following what you're saying. The reason why I did it like this with an isotropic strain and size, and I was happy with it, let's say, and I left it at that, is because I got a decent fit basically like this. I tried introducing preferential orientations for both strain and size. Did not really get an improved fit, but all of the analysis I did on the complete diffractogram and not line by line like you're proposing. I did not see the reason to do so.
The reason is because as you mentioned, this microstructural effect that could have an effect then in the way you can densify your powders and so on, as you mentioned also afterwards. It is to really discriminate between different size and strain effect according to the crystallographic planes. And so theoretically you have different line broadening or asymmetry or things like that in your pattern. Okay. Yeah. So I thank you, Theo, for this very interesting and very interesting discussions, and I congratulate you for this very nice work and a lot of data and results that I'm sure the next comers in the two groups will use to continue this very nice work. Thank you very much.
Thank you.
Okay, thanks, Laurence. Now we are going to move to Wolfgang Zayer for again asking question.
Thank you. Thank you, Theo, for this great work. And I've been particularly enjoying the structural discussions here. That takes a lot of the points that I wanted to make away. And you know my reservation when it comes to this FDDD. I think I want to go back to some of the fundamentals of ion conduction. Would you be so kind to go to slide 22? Because I think I disagree with you there on something very specific.
Yep.
What you're proposing here on the right, in fact, that with temperature, you change the ground state that your ion is in. No. That would mean with increasing temperature, your activation barrier changes, and that completely defeats the idea of an Arrhenius behavior.
Yes, I agree. I mean, this is supposed to be a very quick and dirty somehow introduction to the topic, to the concept. I'm not saying that I'm changing the energy of the lattice site. I'm just saying that I'm giving more or less energy for this ion to hop. So this is kind of the point that I wanted to make.
So what are you actually changing when you increase the temperature?
I'm sorry?
If you think of your equation for ionic conduction, what are you changing by increasing the temperature?
You're changing the KT, the energy, the average kinetic energy that each ion has in the structure.
So you're pretty much just changing a Boltzmann probability for an ionic jump.
Yeah.
Okay. This activation volume is something that bothers me in many ways in an understanding, and it's just that I think we really don't understand what the activation volume is. The way you draw it schematically is purely based on the idea that it changes the transition state and that this is only related to the transition state.
Yes.
Now, if you derive it, you have an isothermal compressibility in there, which would also mean that at higher pressures, you're sort of squeezing your atoms as well. And we know that structures, and especially locally, coordinations can change under pressure. Why are you saying this is only related to the transition state and not also the initial state?
I agree, first of all, with the first point. I think there's a lot to still go deeper and understand further of what is really the value that we get out of such a plot, right? And this, what I'm showing here is somehow a summary I've made from all the literature that I've read on the topic, right? So I'm not saying necessarily that is the end all be all of what we can say. Indeed, when you apply pressure, you will change the phononic behavior of your material. You will change all the modes, right? You will make this is typically captured by the Gruneisen parameter. Basically the deviation of the lattice modes, the energy of the lattice mode or the frequency with a change in volume, which we can then relate to the compressibility because we change the volume when we change the pressure. And there are some models in the literature, old literature from the 60s, 70s, where people are trying to develop such things. The limitation comes to what can we actually measure and what can we actually see, right? At least when we're talking about experiment, then there's definitely a lot of work to do also on the computational side.
You mentioned a Gruneisen parameter. For me, a Gruneisen parameter is a factor of enharmonicity. Right? We usually draw these harmonic potential wells. Ionic jumps must be intrinsically enharmonic. So how does the enharmonicity come into play here in the activation volume? Or how can I envision or visualize the fact that there's some enharmonic contribution when it comes to this derivation of the activation volume?
I'm not sure I have an answer for that. What I will say is that the Gruneisen parameter, I mean, that is one interpretation of it, but from trying to read more and understand what people mean when they say it, I've gotten more confused than I was in the beginning, to be honest. So a lot of people there's multiple equivalent mathematically definitions, and I'm still trying to wrap my head around it. So I don't have a direct answer to that, but the Gruneiser that I'm referring to here is not I should say, the overall Gruneisen parameter of the material, right? Something you would, let's say, quantify with the heat capacity and the speed of sound and so on. It's the mode specific Gruneisen parameter. You can define a Gruneisen parameter for each mode specifically, and here we're interested in the mode that actually carries the ion over the transition state. So this mode, I guess the enharmonicity of that mode is what's important, but deeper than that, I'm not sure I can go at this point.
Okay, I think along that line, if it really is the enharmonicity of that mode, it's most likely only related to the transition state. but I'm pretty sure we're also, for some reason, changing the initial state. And to distinguish those experimentally, this is really challenging. I think in many ways, maybe not in the structure, but in many structures, you can distinguish between at least metastable states and ground states by temperature-dependent diffraction. Here, you pretty much only have one stable sodium site, so looking at site occupancy evolution is not going to do you much here. And another question, now that I see this plot, you have here the activation energy, like EA, right?
Yeah.
Often earlier you showed EM. What's the difference?
In the manuscript, you mean?
In your thesis, and so on. What's the difference between EA
there's no
and
difference.
EM?
I mean,
are you sure?
Sometimes you break the activation energy into the migration and the enthalpy or energy of formation in any case of mobile defects. And for these days, let's say in the popular literature, we're really mostly talking about EM. We're not considering that we're making defects in this material. We consider that these are somehow in the extrinsic regime.
Okay, so it's your measured activation barrier is really the migration enthalpy plus 1/2 of your defect formation enthalpy.
Yes,
the question is, how does your defect formation enthalpy change under pressure? Because now we're here at really high pressure.
So basically you can play the same game with the volume. You can have an activation volume for migration and an activation volume for defect formation. So I think where you're going with this is that this activation volume and this difference that we see here could also be linked to formation more than migration, or?
Correct.
Yes, I agree.
Okay. Another thing that I found really interesting, and this is on slide in your thesis on page 118, and you quickly showed the phonon DOS earlier as well, where you show that they sort of like your phonons flattening out at higher temperatures. This you just showed, but when you directly compare your ball mill and the high temperature NPS, just the phonon spectra, you have there you go. In the high temperature phase, one can still say, okay, there's specific peaks at lower energy phonon modes. So the one between 60, 70, this will just be your PS4 vibrational unit. But lower, you still see sharp features for your high temperature synthesized material. You don't see that in the ball mill material, even though they're the same structure, and I can't understand how macroscopic strain changes the phonon dispersion this significantly. Do you have any idea?
First of all, this is the tetragonal sample, right? So between these two, there's not much macro strain, but there is significant difference in the micro strain. So that is from crystallite to crystallite, there is deviations in the lattice parameters.
How would that change the phonon dispersion curves and like your phonon density of states?
I mean, all I have is a hand-wavy disorder argument, I think. So these modes down here that are significantly broadened. Oh, he's drawing.
I'm drawing, yeah. Like I even see in the lower one, I see one mode. In the upper one, you could potentially see two. So I'm still baffled.
Yeah. I mean, I'm not sure. We've discussed this already. I'm not very sure how to interpret this either.
Okay.
Could this be that? No. I'm gonna say bullshit here.
I think you actually gave the answer already. If you're talking about microstrain, that each crystallite has a different lattice parameter, you're just like really getting a larger ensemble, and that's why it's.
But I thought you didn't believe that answer. Okay.
If you have nano domains, you can explain it.
What?
Nano domains.
Yeah. Yeah, I mean, overall, yeah, this disorder, microstrain, smaller crystallite size, I guess, it all comes together.
Okay. I only have one final question, because this could potentially start a larger argument. You sort of hinted at this, and you also have it in your thesis, the idea of polyhedral rotation helping or like facilitating sodium ion movement. Can you elaborate and can you explain to me how this would even help a conductivity?
I mean, yeah, I love this discussion, but yeah, it's a long discussion, a lot of things to say. When you ask openly like this, can go into a lot of different directions. So these sort of arguments came up first in the 70s, 60s, again, with this paddle wheel sort of visualization where you have this rotating paddle and it kicks your sodium and it moves on, right? But this is quite a naive way to see and understand it. I'm going to try and be succinct here. I understand this paddle wheel and the relation between rotation and of tetrahedra and ion diffusion as really a chicken egg situation. That means you cannot say one causes the other or the other causes the one. It's simply a state of matter where the two coexist. I think I'll leave it there unless you want to pick on that more.
I think in the interest of time, I'll leave it at that.
No, but I won't leave it at that. It's just one minute. Obviously, I will describe it as a kind of motion of ions and polymer. You take polyethylene oxide, it's kind of more or less the motion of the polymer that creates some empty space to drag the ions. And here is the same thing. You have this kind of, turning of the PS4 that are dragging this flow volume to the tank. Maybe it's naive also.
I would have a counter argument to that. So we think that these polyhedral rotations, they're thermal motion, right? Random thermal motion. And so if one rotates, it drags the ion, that I'll give. But now if we actually in an applied field, we want the ions to move, if we measure conductivity or we drag ions through it, we want the ions to move in one direction. So a rotation in this direction will facilitate the ion jump, but it's a random thermal motion. It can also rotate in the other one. At best case, it would cancel each other out. At worst case, we would have something like a phonon drag acting on the sodium ion. Or is that a naive way of thinking from my side?
I don't know.
I don't know either. I think this is a topic that has been discussed since the 70s, as Dio already mentioned. I'm not fully understanding the benefit of this effect, except for the fact that maybe locally you have a higher tracer diffusion coefficient, but once you're at an applied field, does this actually do something to a conductivity?
Yeah, it would somehow presume that then all your paddle wheels start turning in the right direction if you were to help, right? Like an actual mill. Yeah. But I agree that this does not. But I mean, if you think of it, what I'm challenging also with this chicken egg argument is why is it not the sodium that is pushing the PS4 around, right? Why is it not that the sodium in this case, right, needs to go through and it needs the sulfur to move out of the way, so it flips the PS4 around?
I mean, there's work by Don Siegel showing that it's both,
yeah,
right, for a lithium-3 PS4. Oh. Okay, I think I'm done with my questions though. Thank you.
Okay, thanks a lot for Wolfgang. So anyway, I think we are kind of getting later, and still, I'm going to ask question, but still, okay, for me, I think, the presentation was, I think, excellent, okay, and I think you have a great maturity, but I was very deceived by your manuscript. For me, your manuscript is a patchwork of articles without any connections, and I think it's a pity that you didn't make the effort to tie everything together, because you could have a very beautiful document. And don't forget, in life, writing remains, okay? And words are flying. So I think, writing is important, and I think I was deceived, to tell you the truth, but whatever. Now, regarding the question, a lot has been asked, and I will, due to time, limit to a few of them. First, just a comment that I like your sentence. When you talk about synthesis of lithium, thiophosphate, and THF, you have this beautiful sentence: the method is deceptively simple. Can you explain me this sentence for a chemist?
For which method?
Is deceptively simple.
Deceptively simple.
Deceptively simple means.
No, I know what this means, but you think that a chemist, when he finds a simple method, is deceived?
I don't understand the question.
Okay, the question is, okay, you can read it, you will understand. It's page 21. Page 21.
Excuse me.
Yeah. When you talk about the synthesis of lithium, the procedure to produce.
Right, it's deceptively simple because, I mean, what is the simplest way to make something? You mix it's the two reagents, like a solid state synthesis. You would put Li2S and P2S5 in a tube and heat it. That is simple. So it seems like you're doing the same thing in HF.
I just found what you are a chemist. You are very proud when you find something simple. Whatever. Then I think, you talk about ball milling. There have been a lot of questions about Williamson Hall and so on, fine. But you talk about compressibility. You never talk about porosity. How does porosity change when you put pressure? No idea at all. And I would like to know about this stuff. And also the figure that I think is important in page 126, I think, where you compare this kind of different type of pressure. I think this stuff should be enlarged. This figure S14F. This is for me very important. And I cannot even read how much pressure I have since the scale is so small.
Okay. I think I might have it here.
It's about the 132, excuse me.
I think you're referring to this one.
Yes, the figure 1F, Why you don't put a zoom here? Because I think it's very important to see when you look at the intrinsic consolidation. I don't even know how much pressure you apply.
Well, the pressure range here is the same for all. I mean, indeed, I was trying to make this somehow digestible, but this is the best I could come up with, I guess. So the pressure scale is always the same, 1.6 gigapascal. It goes in the increasing pressure on these three, and it goes decreasing pressure on these three. So from 1.6 to 0. And this is simply an over putting all of them together, basically, just to show that as soon as I have a bit of pressure, I'm playing in this intrinsic regime, which is reversible, yes. And then the variation I see is really up here. And yes, it can be attribute densification. What I can say on that front is that no matter how you make your Na3PS4, you can densify it very easily into a pellet of about 95 or more % densification. This is the reason why I propose this different word here, consolidation rather than densification, because from 95% you do not have much room to densify. I think you might agree. And even if you could simply an argument of densification, as in, I don't know, like a Brugman model of porosity in the material, could not explain one or more orders of magnitude of increase in conductivity. So there is something more than just I'm eliminating porosity. In my view, or the porosity that I'm eliminating is not necessarily of the order of I don't know, more than 5%. This is why I made the other figure that I showed, which I call consolidation. did I show it here actually? Yes. I showed it today? Yes. Yeah, here. Where I think that the gaps that you can have that actually block ion conduction do not have to be so large. I mean, you can have a few angstroms of gaps between crystallites and you're essentially blocking all your conductivity. So this is a schematic representation of the picture I have in my head, still exaggerated. You can think that these are a lot closer together, but if you only have point connections between crystallites, I think this can, as an order of magnitude, explain such an effect. Whereas simple densification, I think in the common sense, it cannot.
Okay. Okay. And just a question, and you give me an answer very fast. How, it has been asked in a different way. How can you be sure when you do ball milling, you don't have amorphous, especially at 250 degrees C? What is your argument that you can tell me 100% I don't have amorphous?
An amorphous Na3PS4 phase, you mean? Or
because people ask about the composition and so on. What is your strongest argument?
I have Bragg peaks. I don't know. I mean, I have Bragg reflections, that is crystallinity, and I do not see in any of our investigation any sort of sign of let's say two phases, like, because even if it was amorphous, it should have some characteristic that differs from that of the crystalline beta phase. Okay.
Okay. Okay. Then after I moved, I really like your very short chapter on the solution chemistry. Because number one, I like the comparison that you are making between OH minus, SH minus, all the kind of phase, and even the diagram that you put together. And then after, I was wondering, why didn't you use ionic liquid to remove water?
Why didn't I use what?
Ionic liquid to remove water.
I simply lack the expertise, I guess, and nobody gave me the idea. I don't know what that actually even means. How do I is a hydroscopic ionic liquid?
Yes, because you're hygroscopic, and we have been using quite a lot in order to dry some compound.
Well, I mean, it was the same, I guess, then the same idea as what I did with ethanol, right? So
yeah, but,
I might say that ethanol might be simpler, cheaper.
And I think, and looking at your synthesis, your explanation, an idea came to my mind. Can I make lipon the same way, an aqueous solution? Because in this case, I can really use phosphorus nitride or trifosphorus pentanitride, T3 and 5, and I could really trigger the similar kind of reaction. And I am wondering if I could, in this case, do PO 4 minus X and X. What are you feeling about this stuff?
What I know for sure is that Li3PF4, so somehow the mother phase of lipon, let's say, does not form a hydrate. But I mean, you can definitely dissolve Li2O or LiOH. You can definitely neutralize that with phosphoric acid and add some sort of nitrogen. I'm pretty sure you will get an amorphous phase dropout. Probably not a hydrate, because I'm just thinking because Li3PF4 doesn't form a hydrate. And I mean, yeah, it sounds possible. If you will have the same properties and structure as thin film lipon, I'm not sure, but
no, because lipon, yes, I think it's quite interesting. And then one of my last questions is directly relating to the last chapter. You mentioned, I think, the phase Na3 SN4. You have a pattern at the gamma phase, and there is no index of this pattern. You don't know what it is. What is the limit cell? Do you have any idea?
I have no idea. We're trying to solve that. This is a material provided by a student of Wolfgang's in Gießen. Where is it? But it's I want to show it actually.
Yes, I think it's in page.
It's this, no?
Yes, it's in page, I think, 195, I think. 195, I think. Yes.
Yeah, so this is the overall diffractogram. I just want to highlight that we have another case of this weirdness happening at high temperature close to melting, and many more peaks than what you expect for the low temperature phases. So
yes, right, yes.
Again, a drop in symmetry upon transition to a high temperature polymorph. So a lot of similar characteristics to the gamma in A3PS4 phase, but here even more of a mess, even more peaks. You see, this is already orthorhombic, right? So I cannot imagine how much lower this can be. If you have any ideas, I think we're open for sure. But yeah, to answer your question, I have no idea what space group I can fit this in.
And just a question for curiosity. Do you have any idea what is the energy rotation energy of this PS4 units?
The rotational energy. Entropy. I guess not directly in energy units, but I mean, if it helps, there were some molecular dynamic simulations that I mentioned were done based on our structure, and in terms of time, they figured out that the complete rotation should take about 50 picoseconds. So I guess you can translate that back to a kinetic energy. I haven't done the calculation.
Okay, so anyway, thanks a lot. I will stop here. And again, I think your work is excellent. And again, if you want your thesis to be a Bible, you need to reshape it. It's up to you.
Thank you.
With this, I will give the floor to Jean-Noël, who is really now close to the work, and you can really speak.
Thank you, Jean-Marie. I thank you, Christian and Saiful, also for inviting me and Theo for inviting me for your defense. Well, I was a bit part of the thesis, so I'm glad to be here. I will be very quick. So we heard a lot that we heard a few that the manuscript was a bit unusual, but you are an unusual student. So I could not expect something different from you. And to be honest, I liked it quite a lot. It was different, and we do not see that very often. So at least you have this singularity. And everything started with the very first prologue, which I liked very much. You will be a PhD student. You are a PhD student. You will have a PhD, Doctor of Philosophy. And what you did at the very beginning was almost some philosophy. So I like that a lot. Well, I think that we all agree that you have a very high understanding and you are mastering a lot of different techniques, and especially crystallography and diffraction methods. There is no doubt, but also solid state chemistry, thermodynamics. Your bibliography literature was also so complete, with papers from late 19th century, I guess, 1885, the oldest one, if I remember well. And you also did PDF, spectroscopy, calculations, I mean, a bunch of different techniques, which you are not only using, but I think really mastering, which is not the same thing. And you also show that you could supervise students, 2 of them during your master students, during your PhD, and among them, 1 will continue a PhD students. Okay, so I didn't know about Ernest.
Yes, Ernest as well.
So Adolfo will continue on this very same subject about the antiperovskite here with us. So you trained them well, I guess, and you gave them also the will to continue research. So thank you for that. And well, I could continue for a long time. Thank you for the work you did. Thank you for everything we shared together. And I'm sure you will have a bright future in front of you, waiting for you. Just take it. Thank you.
Okay, thank you, Jean-Noël. So now we are going to move to Saiful, Islam.
Right, I'll start the video. Thank you, Jean-Marie, for chairing this jury. And well, first of all, I have to congratulate Theo. It's now many years since Christian and I interviewed Theo, and we managed to drag him away from Bordeaux, and we've never regretted it. It's been a joy working with you. Regarding the thesis itself, I agree with several points. I mean, it is a thesis that comes from your character, and I enjoyed reading it. But I think you should take on board some of the comments about the structure. I think they were fair comments. But overall, the work that we've done together with Christian has been really strong. You've been one of the strongest PhD students I've ever had, and I'm exaggerating. You've been very independent. You've always been full of good ideas. And as with any good scientist, you're always asking questions. And not only asking good questions, but also trying to address them. So that's why we've had some quality publications out of it, and I'm sure hopefully one or two more to come. So overall, a really strong achievement, and I have to congratulate you. I'm sure you'll have a bright future ahead of you, and I'd be happy to support you in any way I can in that future. So thank you, Theo. Thank you.
Okay, thanks, Saiful. It was nice. And now I will leave the floor to the last, your director, Christian.
Thank you, Mr. President. Thank you, Jean-Marie. And first, I would like to thank you all the colleagues who have agreed to be part in this very impressive jury, who, like Theo asked, he asked for offense. It was not offensive, but it was indeed a real defense, a real PhD defense. And you answered very nicely to all the very difficult questions that were asked by the jury members. Thank you also all for having been understanding for the timeline regarding this PhD defense. We are all suffering a little bit from all these things around the COVID, and this has been a challenge to put all these things together, given the situation and given the difficulties related to the mobility and the fact that Theo was actually not in Amiens and was confined in Germany and then in Switzerland. All things together, it is I appreciate also that jury members have been understanding in the timeline to put all these things together. Theo has made a last slide acknowledging the institutions who funded the work and with which he had been collaborating. I would like to be a little bit more personal in the people who have been involved in this work. It is very important for me to put people behind the institutions. And of course, I first like to thank Saiful in Bath for this very nice collaborative work. And I will never forget, I will not forget to associate Piero Canepa and James Dawson, who have been heavily involved in all the work related to computational screening of these inorganic electrolytes. This has led to the masterpiece of Theo in his review paper published in Nature Materials. And I can really witness that all this project, because it was actually a project, has been led by these young people, Theo, James, and Piero. And with Saiful, we were just trying to help them. It was really a deep study and a lot of work. I would like also to thank Wolfgang in welcoming Theo for the 4th year. It was also unusual, as Jean-Noël said, but Theo wished to go deeper, even deeper in his studies. And so we had the opportunity to travel to Germany in a very prestigious lab on solid electrolytes and ionic conductors and solid batteries. I think it was a very good choice. You maybe didn't get as much as you expected because of the COVID, and you couldn't do all the experiments you dreamt to do over there. And from March, you were not in the lab. So, but thank you, Wolfgang, for welcoming Theo. And I know that you had many interesting and challenging discussions with him. Our colleagues from ALBA, ILL, and ISIS are very much acknowledged. We are lucky to have access to large-scale facilities, and we have good friends in all these places, and this is very important. And François Faute in Alba Barcelona, and Emmanuel Suar in ILL in Grenoble, and Mohamed Zbiri in IL Grenoble as well, have opened the doors. We have made proposals, of course, but also they were able to measure samples for Theo with Theo over there, and this brought a lot to the thesis. And also, Theo was fully involved in measuring, analyzing, and all the things that were done in the large-scale facilities. Oliver Clemens in Darmstadt also participated to this work. Of course, he introduced us to Ernest, who made the master thesis with us on the antiperovskites. This brought a lot. And also he participated to some of the work in the analysis. And Damien Dambournet in Phoenix in France, in Paris, also participated and helped a lot in the PDF data acquisition and analysis and all things. Some colleagues from Cambridge also. So it is a really big project overall. It is also, but I would like to stress, Theo was in the center of it. He was the leader, the project manager of his PhD thesis. And this is impressive how he was able to handle all these people. And in his last paper published in JACS, there is an impressive list of authors because many people tried to help and helped in getting this very puzzling thing about Na3PS4. So I think it's just really impressive the way he handled managing and getting all these inputs from many people all together. And maybe from that, the PhD thesis writing in a standard way suffered a little bit. But I have to say, and I fully agree with Jean-Marie, that writing is very important. And overall, already Theo has been involved in 10 research papers published. So I think it's very difficult to do more than what he did in terms of writing, especially that he wrote most of the papers himself. So this has to be pointed out, even though the PhD manuscript is not as a normal standard as we would have expected. He decided, and I supported him to write his PhD thesis as a collection of papers published, plus very interesting perspectives, which are not completely finalized. As you mentioned about Li3PS4, but the aqueous synthesis of solid electrolytes, which will have also very strong impact in the future, I think. I would like then finally to thank local people, because this is very important, in Amiens, in LRCS, and those people in particular involved in the solid-state battery activities, Vincent, Virginie, Mathieu, Raphaël, and Jean-Noël. So we exchange a lot with all these colleagues, and they have been involved in some parts of Theo's research, and this is very important, at least also in terms of the support for the global activity in this new theme in the lab. I will not forget Oulash, Cédric, and Xavier, your PhD co-workers. Oulash has already defended, and Cédric and Xavier will defend soon, and some other PhD students, of course, of the lab. And last but not least, I would not forget Nathalie, Daphne, and Anne, who had to support Theo, who traveled a lot in many places. So this brought a lot of work also for these ladies who were very patient with you in supporting your trips and your administrative burden sometimes. Okay, so then Theo, I think I have said a lot about your work and everything. I would like to highlight a few things about your character and about your activities. The very impressive thing that we all have to acknowledge is the superb, impressive global knowledge of the literature Theo has. This is truly amazing. I would invite all of you guys in the jury to share the Mendeley bibliographic database that he has gathered. This is fantastic. I would really, and as I do like to go to bibliography, I was really impressed, not even by the amount of papers gathered, but the fact that they were all studied with highlights, with yellow highlights on these papers. That means he reads them. So I don't know how he does that, but he reads all the papers he's mentioned. It's very important. So I would just say that he's a truly passionate scientist, really a real scientist. So I think and I hope that you will make your way in continuing to do science in the future. This is not an easy path, you know. This is there are pros and cons about really thinking about entering in academia, but I think you have the strength of it, and for sure the scientific passion. You have been fully focused on your PhD work. I am really, really, really impressed by all what you did, and that's all what I have to say for today. And the other things will be in private, with a cup of champagne, I hope. Thank you, Theo, for everything you did.
Okay, so thanks, Christian. I think you cover everything. I don't even know if we have to meet together to discuss now. Anyway, yes. So thanks again, Theo, because it was nice. I am sure you are sick of it. And let's try to stop it, and we are going to discuss and not to hold you too much, I guess.
Yeah.
Okay, thank you again.
Thank you. We'll go out of the room and we'll just make a small meeting of 5 minutes to gather things and maybe declare him PhD owner at the end.
Eventually.
Okay, so